This is lecture number 2, Patterns with Counting Numbers. As we saw in lecture 1, a counting or a natural number are the numbers that really appear in life. That is 1, 2, 3, 4, 5, so on and so forth, all the whole numbers greater than 0. The first pattern we're going to look at is something called a palindrome. And a palindrome is a word or a number that when you write it forwards or backwards, it has the same meaning. There are words, there are names actually, that are palindromes. Anna, Otto are names that are backwards, are Anna and Otto. Radar and race car are two examples of words that when you write them forwards or backwards, they are the same. A classic palindrome sentence is a man, a plan, a canal, Panama. If you write that backwards, it's a man, a plan, a canal, Panama. What it means, we're not sure, but it is a palindrome. Palindrome numbers are very interesting. An example of a palindrome number would be 33, because if you wrote it backwards, it'd be 33. 414, 8,778, and 10,401 are all palindrome numbers. What's interesting, and one of the things I discovered because I'm always looking for patterns using mathematics as in our world around us, is some years ago I taught in a building that was built in 1991. And when you entered the building, on one side of the doors there was a 19, and the other side of the doors there was a 91. And 1991, the year, is a palindrome number because written backwards it's 1991. The question is, what's the next palindrome year after 1991? Well, 2002. Now, there are quite a few of us who expect and were around in 1991 and in 2002. So therefore, someone alive in 1991 had a very good chance of seeing a second palindrome year. I'm not sure if it's reason for celebration, but it's quite significant when you consider the previous palindrome year to 1991 was 1881, which means a person who, let's say, was 5 years old in 1881 would be 115, assuming they were still around and could understand what year it was, to recognize that they were in their second palindrome year in 1991. And the next palindrome year after 2002 is 2112. Again, another 110 years. In fact, it's only a change of the millennia when you had the rare opportunity, those of us who care about mathematics, to see two palindrome years in a normal lifetime. Now, again, for some people, that might matter a great deal, but to me, it was an exquisite discovery as I recognized this and passed it along to all my students. And most of them didn't think it was quite as exquisite, but it was interesting, certainly, because they could appreciate that they were special, and, for example, their great-grandparents and great-great-grandparents never had that opportunity. Well, what's so special about palindrome numbers other than 1991? Well, let's take a look at a number that's not a palindrome number. 142 is not a palindrome number. If you write it backwards, it's 241. But notice what happens if you add 142 and 241. You get 383, which is a palindrome, since 383 backwards is 383. A mathematician would ask, does this always happen? If you take a number that's not a palindrome and reverse the number and add it to the original number, do you always get a palindrome? If you start with 251 and reverse and add, that is, add 251 to 152, you get 403. If you reverse 403, 304, and add 304 to 403, you get 707, which is a palindrome. The question that must be answered is, will all numbers under the reverse and add process always eventually become a palindrome? Well, let's consider some two-digit numbers first. All the two-digit numbers, you have multiples of 11, 11, 22, 33, etc. Those numbers are palindromes. Some of the two-digit numbers, such as 18 and 34, become palindromes after one reverse and add cycle. Other two-digit numbers, such as 57, for example, take more than one cycle, and 89, or 98, takes more than 20 reverse and add cycles to finally obtain a palindrome. And all of those two-digit numbers will eventually become palindromes by adding and reversing, or reversing and adding, I should say. That is reversing the number and adding it to the original number. It is conjectured, I said, that all counting numbers will eventually become palindromes under the reverse and add technique, even though for some numbers it may take more than 30 cycles to obtain the palindrome. This conjecture, to my knowledge, has not yet been proven for all counting numbers, which means there may be a mathematician out there, a number theorist, who is spending his or her days and nights and weekends trying to prove that's true for all numbers. Again, you may say, I have better things to do with my time, but this is a passion among mathematicians. And you may even say further, what good is it? When will we ever use it? And the example I always give is with codes. To create codes using numbers, if there's some patterns, you can use those patterns to allow the person decoding a message to know what part of the message really is to be decoded and what part of the message is just stuff to confuse the person who should not receive that message. Now, there's another kind of process that leads to another kind of number called a black hole. What is a black hole? Well, Dr. Stephen Hawking, possibly the greatest brain alive on Earth at this moment right now, wrote some books, and if you haven't read the books, you might want to do that, but he talks about black holes. A black hole is a location in space that is so dense that the gravity is so strong that not only is all matter sucked into the black hole, but so is light, and that's why it's called a black hole. Well, what does this have to do with counting numbers? Well, let's start with the number 6,174. That number was selected for a very good reason, because we write the largest number, the largest four-digit number we can write using those four digits, and of course that's 7,641. We then take and reverse that number, writing the smallest four-digit number we could write with those four digits, 1,467, and we subtract. And guess what? We're back to 6,174. We are in a black hole since there is no escape. If we do this process again and again and again, we'll always wind up with 6,174. What if we start with 3,870? What is the largest four-digit number we could write? 8,730. We reverse it, and we obviously have the smallest four-digit number, 0378. If we subtract, we get 8,352. The question is, what happened? It's not a black hole. Well, certainly not. Or is it? Do we know? Well, it's not 6,174, but let's find out. Let's take that 8,352 and write the largest and the smallest four-digit numbers, 8532 minus 2358, and guess what? We're back to 6,174. If you start with any four-digit number other than one where all the digits are the same, obviously you start with 3333 and subtract 3333, you're going to get 0. But any other four-digit number, and do this process, write the largest four-digit number using those four digits, subtract the smallest four-digit number using those four digits, eventually, through that process, you will get to 6,174, which will be a lock, a black hole. You're stuck and you can't get out. How about three-digit numbers? Starting with a three-digit number where all the digits are the same, all the digits are not the same, we do the same process. We take the largest three-digit number we can write with those three digits, subtract the smallest three-digit number we can write with those three digits, and eventually, and fairly quickly, we get to 495, which is the 6,174, the black hole for three-digit numbers. It's interesting to note that both 6,174 and 495 are all multiples of 9. The question a mathematician would ask is, how about five-digit and six-digit and seven-digit numbers? Are those black holes multiples of 9? Again, if you're not a mathematician, you may not have interest in this. It might be interesting that this occurs, but you wouldn't want to spend your time investigating it. A mathematician would become passionate about investigating this. Now, the point being, again, is that if you take any number that is other than a number where all the digits are the same, and you write the largest number and the smallest number you can make with those digits and subtract. Eventually, you will get to a black hole. Another interesting pattern involves counting numbers with their cubes, that is the third power. So taking a number, multiplying it by itself and multiplying it by itself, but looking only at the 10 digits, 0 through 9. And each of those obviously has a cube. 0 cubed is 0, up to 9 cubed, which is 729. What we investigate is the sum of the cubes of the digits of various counting numbers. If we start with 43, 4 cubed is 64. 3 cubed is 27. We add those two up, the sum of the cubes of the numbers, of the digits in the number. 64 plus 27 is 91. Well, you say, well, big deal. Okay. 91, we take the 9 and cube it, 729. We take the 1 and cube it, 1. We add, we get 730. 7 cubed, 343, plus 3 cubed, 27, plus 0 cubed, 0, is 370. And you'll notice that 370 and 730 are the same digits, and therefore 370 is a lock. When we take the cube of 3, the cube of 7, the cube of 0, add them up, we get 370. We are stuck in a lock. Okay? If we start with 207, a 3-digit number, the sum of the digits are 8 and 0 and 343, equaling 351. Continuing this process, we get 153. So 153 is a lock because 153 and 351 contain the same digits. If we start with 43, a 2-digit number, we get locked at 370. There's a number of digits indicate the lock number. If we start with 16, the number of cubes, the cubes is 1 cubed is 1, and 6 cubed is 216. We get 217. 217. 2 cubed is 8. 1 cubed is 1, and 7 cubed is 343. We add those up to get 352. Continuing the process, we're back to 160. We say we didn't start, we started with 16, but remember, 16 and 160 are equivalent because the only difference is that 0 and 0 cubed is 0. So what we have is now what's called a loop. We're in a loop, 160, 217, 352, back to 160. We never get out. Kind of like that black hole, but it's a little different because now we're dealing with the cubes of the digits. And there are 5 numerical locks. That is, in all the whole numbers, in the infinite number of whole numbers, if you start out with any whole number, as many digits as you like, and you add up the digit, the sum of the cubes of the digits in that number, and you keep doing that process, you will eventually get, if you get to a lock, to one of these 5. That's it. Those are the only 5. There are no other locks. And you'll notice 2 of them are adjacent numbers, 370, 371. Now, someone who was really passionate about this might say, well, why? And spend the rest of his or her life investigating these. There are also loops, and there are 4 loops. That 2 of them involve 2 numbers. If you get to 136, you go to 244 and then back to 136, stuck there forever. The 919 and 1459 is the other 2-number loop. And then there are 2 3-digit loops, 2 3-number loops, which are 160, 217, 352, and 250, 133, 55. Now, therefore, for any counting number, if you use this process, the sum of the cubes process, you will wind up with either one of the locks or one of the 4 loops. And that's it. There are no other choices. Now, one thing that is interesting to pursue is taking a look at numbers that all the digits are the same. Remember, in black holes, we couldn't deal with these because when we subtracted, we got 0. But let's take, for example, 111 or 222. And I had a class one time that did this. And what was amazing is that all the 3-digit numbers, other than 000, but 111, 222, up to 999, all locked at 153. Every single one of them. So then I supposed, let's look at 2-digit numbers, thinking like a mathematician. And the two-digit numbers do not all lock at 153. The only three two-digit numbers, where both digits are the same, that go to 153 are 33, 66, and 99. So is there a pattern? All of the three-digit numbers, 111 through 999, where the digits are all the same, go to 153 in this process. Only 33, 66, and 99 among the two-digit numbers that are made up of two digits that are the same go to 153. What is special about these numbers? It turns out that all these numbers are multiples of 3, since three-digit numbers that are made up of the same digit are 3 times something, and 33, 66, and 99 obviously are multiples of 3. In fact, any and every multiple of 3 that you can try this process with will go to 153. So we've just seen 3 examples of simple arithmetic, adding, subtracting, and multiplying with adding, patterns that are interesting. Again, if you're concerned with recognizing the patterns and maybe even asking questions about the patterns. Patterns and sequences of counting numbers abound. Some are quite useful, others are simply to be enjoyed because of the beauty of the pattern. Okay? There are magic sequences such as 7, 11, and 13. If we take a number such as 368 and multiply that by 7, multiply that answer by 11, and then multiply that answer by 13, we get 368,368, which is really a kind of a cycle of the original number. And the interesting thing is, will this work for all numbers? And the answer is yes. Why will it work for all numbers? Well, take a 6-digit number, such as 925,925, and divide that number by 7. Take the answer and divide that by 11, and then divide that by 13, and you'll be back to 925. The final result is the 3-digit number that was used to make the cycle 6-digit number. What is significant about 7, 11, and 13 when you're multiplying or dividing? Are they magical numbers? It's not magic. 7 times 11 times 13 is a product of 1001. If you multiply a 3-digit number by 1001, the 1 times the 3-digit number gives you the 3-digit number, and the 1000 times that 3-digit number gives you that 3-digit number in the 100,000s, 10,000s, and thousands place, thus giving you that cyclical appearance. And of course, if you divide, it goes the opposite way. So they're not magic numbers, it's just that 7 times 11 times 13 is 1001. One of my favorite topics, other than mathematics and history, is baseball. And back in April of 1974, while I was living in Atlanta, Henry Hammering Hank Aaron hit his 715th Major League home run, thus surpassing George Herman Babe Ruth, who had hit 714 career home runs in the Major Leagues. A mathematician who was a baseball fan and who worked at the University of Georgia and obviously was a Braves fan, saw a pattern. I mean, again, it's hard to imagine someone watching someone breaking a long-standing record and saying, wait a second, I see a numerical pattern there. But he did. What he recognized is that if you multiply 714 and 715, and you multiply them by each other, you get 510,510, which means we now know those numbers are divisible by 7, 11, and 13. If you divide by 7, 11, and 13, you wind up with other factors of 2, 3, and 5. Now let's see. 5, 2, and 3, 7, 11, and 13. And the final factor you get is 17, which means that 510,510, the product of 714 times 715, is 2 times 3 times 5 times 7 times 11 times 13 times 17, which are the first 7 prime numbers. So the product of 714 times 715 has a unique, as all numbers do, a unique product of primes which contains the first 7 prime numbers. What this mathematician said was any 2 adjacent numbers, that is 2 counting numbers that one comes after the other, like 714, 715, whose product is equal to the product of a consecutive primes, are to be called Hank Aaron numbers. It turns out that 5 and 6 are also Hank Aaron numbers, since 5 times 6 is 30, and 30 equals 2 times 3 times 5, the product of the first 3 primes. Leonardo of Pisa, Fibonacci, who we referred to in the first lecture and who we will see again and again, came up with a sequence of numbers that have become known throughout the world as the Fibonacci numbers. We start with 2 ones. A comma separates each term. After those 2 ones, every succeeding term is the sum of the previous 2 terms. So the third term is 1 plus 1, which is 2. And then the next term is 2 plus 1, which is 3, and then 2 plus 3, which is 5, so on and so forth. And of course, the numbers grow rather large, rather quickly. The Fibonacci sequence has applications in biology and in geometry, and of course, again, my favorite, creating codes. So the usefulness of this, simply created by taking a pattern of numbers, was one of the earliest, at least in European mathematics, of looking at a sequence and trying to apply it somehow. And it turns out that there are some mathematicians who love to find situations, especially in geometry, where the answer is, oh, those numbers are the Fibonacci sequence, or part of the Fibonacci sequence. And there's other aspects of the Fibonacci sequence that I will not get into now, but there are whole books on nothing more than the Fibonacci numbers. Really interesting. There are sequences associated with the geometric triangle. There are triangular numbers and Pascal's triangle. Triangular numbers start with the number 1, and then you add 2 to get 3, you add 3 to get 6, and so on and so forth. Each number is obtained by adding the next counting number. So 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, and so on and so forth. Now, why should these numbers be interesting? Well, first of all, why are they called triangular? And that's because if you take 1 dot and then you add 2 dots, it forms a triangle. And you add 3 dots, you have a 3-row triangle. And you can keep adding the next number of dots. 4 gives you 10. So the numbers in the triangular number sequence can be displayed graphically as a triangle arranged with the number of dots for that number. Now, what's special about these numbers? Well, triangular numbers have some interesting uses. For example, in geometry, if you take a certain number of points and draw as many lines as you can, unique lines, through the various points, the number of lines that can be formed is a triangular number. So therefore, if I take, for example, 2 points, which is the smallest number of points to draw a line, I draw 1 line. If I make a 3rd point out there, I can now draw 3 lines, and in fact, it forms a triangle. If I put a 4th point out there, I get 6 lines, kind of looking like a quadrilateral with 2 diagonals in it. But basically, the geometric representation of the number of lines given a certain number of points is part of the sequence of the triangular numbers. If you add 2 adjacent triangular numbers, you get a square number. That is a number which can be obtained by multiplying by itself, but multiplying a number by itself. For example, 6 plus 10 is 16, and 16 is 4 times 4. In fact, this summer, while I was teaching in a honors class for rural high school students in Nebraska, one of my students looked at the triangular numbers. This is a young lady who just had finished 8th grade. And she said, look, if you look at those numbers, if you look at the difference between 2 triangular numbers, that number is the square root of the sum of those 2 numbers. And I've been playing with triangular numbers for a long time, and this was kind of new on me, and the class proved it, and it is true. But again, here was a child who may someday be a great mathematician, and I saw her as an 8th grader. Blaise Pascal was a 17th century French mathematician and philosopher. And he's given credit for creating Pascal's triangle. Actually, the arrangement of numbers that's called Pascal's triangle was known hundreds of years before Pascal's birth. The first row in the triangle has a 1 in it. The second row has 2 ones. Each row, in fact, starts and ends with a 1. All the numbers between the ones, as you progress down each row, is given by the sum of the 2 numbers above it. So you'll notice in the 3rd row, there's 1, 2, 1. The 2 is the sum of the two ones above it. The fourth row is 1, 3, 3, 1. The 3 is 1 plus 2, and the second 3 is 2 plus 1. And again, the row starts and ends with a 1. And this continues ad infinitum. Pascal's triangle goes on forever. There are many patterns embedded in Pascal's triangle. The most obvious is the counting numbers. You can look and see 1, 2, 3, 4, 5, 6 if you're looking at Pascal's triangle. There are also the triangular numbers are in Pascal's triangle. 1, 3, 6, 10, 15. If you add up the numbers in each row, for example, the first row is 1, obviously. The second row is 1 plus 1 is 2. The third row is 1 plus 2 plus 1 is 4. What you're getting are powers of 2. Okay, 1, 2, 4, 8, 16, 32, and this goes on forever. The rows of Pascal's triangle also display powers of 11. 11 to the 0 power, and again, we'll talk about the 0 power because I'm not confusing some people, but that's 1. 11 to the first power is 11. 11 to the second power is 121. And 11 to the third power is 1,331. You say, wait a second. That's the first 4 rows of Pascal's triangle. Is it magic? No, it's mathematics. And what it is, obviously, is that 11 is 10 plus 1. And it turns out that when you multiply 10 plus 1 times 10 plus 1, you get 100, 2 10s, and 1 1. And again, if we had the time, if this was a lecture totally on the uses of Pascal's triangle, we could investigate this further. And it goes on. It's really interesting what happens when you get to higher powers of 11. It's not quite as clear, although the numbers are embedded in Pascal's triangle. But remember, once you get to the next couple of rows, you start getting 2-digit numbers. You got to worry about what we used to call carrying, and now they call renaming or regrouping. But suffice it to say that you can find powers of 11 in Pascal's triangle. Pascal's triangle is used in determining probability of certain events. For example, let's take a look at a situation where you were flipping some coins. Let's say you had a penny and a nickel and a dime. And you say, well, what's the chance of flipping those 3 coins separately and getting 2 heads or 1 head? Or 0 heads, or 3 heads. Those are the only possibilities. 0, 1, 2, and 3. Okay. Well, let's see. How many ways can I get no heads? You say, wait a second, you can't get it. Yes, I can. If I flip 3 tails, I have no heads. Well, let's see. So that's one way. Tail on a penny, tail on a nickel, tail on a dime. How many ways are there to get 1 head? Well, let's see. I can get a head with a penny and tail on the other 2 coins. I can get a head on the nickel or a tail on the other 2 coins. I can get a head on the dime or a tail on the other 2 coins. So therefore, there are 3 ways. Okay. How many ways are there to get 2 heads? Well, 2 heads better than 1, I'm not sure. But the way to get 2 heads is, of course, to get 1 tail. And we just saw that there were 3 ways to get 1 head, so there must be 3 ways to get 1 tail. You get a tail on the penny and heads on the other 2 coins, a tail on the nickel, heads on the other 2 coins, or a tail on the dime and heads on the other 2 coins. So there are 3 ways. And how many ways are there to get 3 heads? There's only 1 way. All 3 coins are heads. 1, 3, 3, 1. But that's the Pascal's triangle. That's the 4th row of Pascal's triangle. 1, 3, 3, 1. And it turns out, guess what? If you flipped 4 coins and you looked at the number of ways to get 0 heads, 1 head, 2 heads, 3 heads, and 4 heads, you would see 1, 4, 6, 4, 1. Pascal's triangle. And this leads to a whole thing which we'll talk about in our lecture on probability, binomial probability. What we've looked at in this lecture is a number of different patterns involving counting numbers. In our next lecture, lecture 3, we'll go beyond counting numbers and deal with rational numbers. Now, some people might think that means numbers that think rationally. If you don't know what rational numbers are, we'll see you in lecture 3 and find out.